In this video, we're going to look at the properties and trends of group 7 elements. So we're going to look at their electronegativity, boiling points, the oxidising power, and the reactions of chlorine. We'll then look at the group 7 ions, so we'll look at their reducing power and the reactions of these ions with sulphuric acid. And finally, we'll look at the test for inorganic ions, summarising what we've covered in this video and in the group 2 metals video. The boiling points of group 7 elements increase as you go down the group. So fluorine at the top of the group has got the lowest boiling point, and we can see the boiling points then increase as we go further down. And this is because as you go down group 7, the molecules get bigger, they've got more shells of electrons. As the molecules get bigger, you can have stronger van der Waals forces between those molecules. Therefore, more energy is required to overcome those slightly stronger forces of attraction, so the boiling points will increase. The electronegativity of the group 7 elements decreases as you go down the group. Remember, electronegativity is the ability of an atom to attract the bonding electrons in a covalent bond. So it's how easily can that atom attract a pair of electrons. So the reason the electronegativity decreases as you go down the group is that the atoms get bigger, as we've just talked about. This means that there's more shielding of that outer electron shell from the nuclear charge. Because there's more shielding, this means those atoms are less able to attract electrons to fill their outer shell. The nuclear force of attraction is weaker because of the more shielding, therefore less able to attract the electrons, therefore they have a lower electronegativity. We're now going to look at the oxidising strength of the group 7 elements. So when halogens react, they gain electrons, which means that they are going to be reduced, because remember, oxidation is loss of electrons, reduction is gain. So if we say that when halogens react, they gain electrons, this means the halogens are being themselves reduced. And because the halogens are being reduced, that means they are the oxidising agents in that reaction. They're being reduced, which means they are gaining electrons, which means they are oxidising something else. They are taking the electron off something else. They are oxidising the other element, therefore they are called oxidising agents. So for example, if we look at the reaction of sodium with chlorine to form sodium chloride, we can see that the chlorine has gone from an oxidation state of 0 to -1. That's a decrease of 1, therefore it's gained electrons. This electron has come from the sodium, so the chlorine has taken the electron off the sodium, the chlorine has oxidised the sodium, and itself has been reduced. Group 7 elements are less oxidising as you go down the group. This is because they are less electronegative as you go down, like we've just looked at. This means they're less able to attract a pair of electrons, so that it makes sense that they're less oxidising because they're less able to take that electron. So we can now use our knowledge of the oxidising strength, essentially how reactive the halogens are, to look at what happens in displacement reactions. So a halogen will displace a less reactive halide ion from its compound. For example, chlorine is more reactive than iodine because it's higher up the group. This means that chlorine can displace iodine from its compound. So chlorine plus potassium iodide would form potassium chloride and iodine. So the chlorine has displaced the iodine. We're now going to look at a series of displacement reactions. In each case, we're going to react the halogen with a halide salt. So remember, the halogen will displace a less reactive halide ion from its salt. All of our halogens are aqueous solutions, so we've got essentially chlorine water, bromine water, and a solution of iodine in water. Chlorine water is colourless, bromine water is orange, and the solution of iodine in water is brown. I'm going to come back to these colours in a moment. All of our salt solutions are colourless as well. So the first thing we can do is say that there's going to be no reaction between the halogen and the halide salt of the same halogen. So it makes sense that the chlorine is not going to react with potassium chloride because it's the same element. The same can be true for bromine and potassium bromide, and iodine and potassium iodide. Chlorine is more reactive than bromine, so chlorine will displace the bromide from its salt, giving us potassium chloride and bromine. Chlorine is also more reactive than iodine, therefore chlorine will displace the iodide from its salt, forming potassium chloride and iodide. Bromine is less reactive than chlorine, so the bromine can't displace the chloride from its salt, therefore there's going to be no reaction in this case. Bromine is more reactive than iodine though, so the bromine can displace the iodide from its salt, forming potassium bromide and iodine. Iodine is less reactive than chlorine, so the iodine can't displace the chloride from its salt, so there will be no reaction in this case. Iodine is also less reactive than bromine, so there will be no reaction between the iodine and the potassium bromide. Now we can also use these reactions as a test for different ions. Let's say we wanted to test for either chloride ions, bromide ions, or iodide ions. We could add one of these samples. So for example, we know that chlorine is colourless, all the salts are colourless, however bromine and iodine are coloured. Bromine is orange, iodine is brown. So let's say we wanted to test for bromide ions. We wanted to see if an unknown solution had bromide ions in there. So if we added chlorine water to our sample containing bromide ions, well, they're both colourless to start off with. However, the reaction would form bromine, which we know is orange. So we would see a colour change from colourless to orange, would have displaced the bromine from its compound, so we would have seen the colour change from colourless to orange. Again, we could also use this test to test for iodide ions. So for example, if we wanted to test for iodide ions, we could either add a sample of chlorine water or bromine water. In both cases, they would displace the iodide from its compound, forming iodine, which is brown. So if we use the chlorine water, the solution would go from colourless to brown. If we use bromine, well, it would start off orange from the bromine water, and when we added the potassium iodide, it would turn brown through forming the iodine. We're now going to look at the process of making bleach from chlorine. So if you mix chlorine gas with cold dilute sodium hydroxide, you'll form bleach, or sodium chlorate. And you need to be able to write the equation for this process. Now, if we look at the oxidation states for this reaction, we can see that chlorine goes from an oxidation state of 0 to an oxidation state of +1 in the sodium chlorate and an oxidation state of -1 in the sodium chloride. This is an example of a disproportionation reaction. If you're unsure about oxidation states and these kinds of reactions, watch the video for 3.1.7 oxidation, reduction and redox processes. If we react chlorine with water, this is also a disproportionation reaction. So this is the equation for this reaction. Note that this is an equilibrium process where the chlorine reacting with water forms hydrogen ions, chloride ions and our chlorate ions. And if we work out the oxidation states, again we can see that chlorine is going from an oxidation state of 0 to -1 in the chloride ion and +1 in the chlorate ion. In sunlight, chlorine gas decomposes to form chloride ions and oxygen. Now this reaction will predominantly happen in the atmosphere, so the chlorine gas will react with water vapour to form hydrogen ions, chloride ions and oxygen. We're now going to evaluate the use of chlorine in water treatment. So chlorate ions, what you find in bleach, kill bacteria. Now this is good because it means that we can make water safe to drink. However, it's also toxic. Now in the UK, for example, we do use this to purify water because it kills the bacteria, it removes discoloration from water, removes smells, and it prevents the growth of algae. However, chlorine or chlorate can also react with organic compounds in water. So for example, it can form chloromethane, which is a carcinogenic compound. It can cause cancer. However, the decision's been made that this is worth the risk. It's quite a small risk compared to the risk from bacteria growing in the water and causing illness that way. There is also a very small amount of these organics in water, so the chance of any one person having a high concentration of this in their drinking water is extremely low. But you do need to be able to evaluate the advantages and disadvantages of using chlorine in water treatment. We're now going to look at the ions the halogens form. So it's important to remember up until this point we've been talking about the halogens themselves as diatomic molecules. So for example, Cl2Br2I2. We're now going to look at their ions, so Cl-, Br-. Don't get these mixed up. So the group 7 ions will react by losing an electron because they've already got an extra electron, for example, Cl-. Since they react by losing an electron, this means they are being oxidised because oxidation is loss of electrons. This means we can say that halide ions are reducing agents because again, they're being oxidised, they're losing electrons, which means they've got to give that electron to something else, which means they're reducing something else, they're making another chemical gain an electron. Now, like we've already looked at, as we go down group 7, you're adding more electron shells, so there's going to be greater shielding, and those outer electrons are a greater distance away from the nucleus. This means that as you go down group 7, the outer electrons experience a weaker force of attraction from the nucleus. Therefore, the reducing power of the halide ions increases as you go down group 7, as it's easier to lose that outer electron. It's easier for the halide ions to give that electron to something else and reduce it. We're now going to look at the various reactions of group 7 ions with sulphuric acid, and their ability to reduce things is really important here. So all of the halide ions will do the same basic reaction with sulphuric acid. This is the general formula for that reaction. So sodium halide salt will react with sulphuric acid to produce sodium hydrogen sulfate and the HX molecule. Again, remember that X represents a halogen ion. Now, depending on the reducing power of the halide used, further reactions are possible. So we're now going to look through the reactions of sodium fluoride, sodium chloride, sodium bromide, and sodium iodide. So as we've just looked at, sodium fluoride and sodium chloride are the weakest reducing agents. So this means they can only reduce the sulphuric acid to sodium hydrogen sulfate, like we looked at the previous example. They don't react any further. Bromide, however, is a stronger reducing agent than the fluoride and chloride we've just looked at. So the bromide can reduce the sulphuric acid to the sodium hydrogen sulfate like we've already looked at. However, the bromide ion can then reduce the sulphuric acid further. So the bromide ion will reduce the sulphuric acid in this case to sulfur dioxide. And again, this is another equation you've got to know, and you've got to explain that this happens because the bromide ion is a stronger reducing agent than the fluoride or the chloride. Iodide is the strongest reducing agent we're going to look at. So it can reduce the sulphuric acid into the sodium hydrogen sulfate. Like the bromide, it can then reduce it further to form the sulfur dioxide. And the iodide can go one step further to reduce the sulfur dioxide into hydrogen sulfide. And again, these are equations which you need to know. We're now going to look at the tests for various ions, both metals and non-metal. So this will summarise the ions which we looked at in the Group 2 video and in this video. We're going to start by looking at the tests for Group 2 metals. So in order to test for the presence of calcium, strontium or barium, you use a flame test. So this involves lighting a Bunsen burner, placing a small sample of your metal on a nichrome wire and putting that inside the flame. You'll then see the flame change colour depending on what ion is present. So calcium will go brick red, strontium will go red, and barium will go a pale green. To test for ammonium ions, the first thing we do is react the sample we're testing with sodium hydroxide. Now what this does is any ammonium ions present will react with the hydroxide to form ammonia gas. This then lets us test for the presence of ammonia gas by using damp red litmus paper, which will go blue. So it's not a direct test for the ammonium ions. However, by changing the ammonium ions into ammonia and then testing for ammonia, we can confirm that there were ammonium ions present. The litmus paper needs to be damp because the ammonia we've produced is a gas, so by making the litmus paper damp, the ammonia will absorb better onto the litmus paper. Ammonia is a base, so we'll see the red litmus paper turn blue. To test for sulfate ions, the first thing we do is add an acid, commonly hydrochloric acid. And this is important because it will react with any carbonate ions. The reason this matters is because if there are carbonate ions present, the barium will form white barium carbonate, which we don't want because that could give us an invalid test result. The next step is to add some barium chloride. And the barium ions will react with any sulfate ions to form barium sulfate. Barium sulfate is an insoluble white precipitate, so you should see that form on your sample if sulfate ions are present. And this is why it's really important that we do the first step, because this prevents any white barium carbonate forming and confusing the positive result. To test for hydroxide ions, we just need to test the pH of the sample. So, for example, this can be done by using red litmus paper, which will turn blue. To test for halide ions, you need to add dilute nitric acid and some silver nitrate. We're going to look at the results for 3 halides: chloride ions, bromide ions, and iodide ions. Chloride ions will form a white precipitate of silver chloride. Bromide ions will form a cream precipitate of silver bromide. And iodide ions will form a yellow precipitate of silver iodide. You can remember it as the colour getting slightly more murky as you go down. So we start off with white, then cream, then yellow. It can be quite hard to tell these colours apart though, so in order to make sure we know which precipitate we've formed, we then add ammonia. The silver chloride precipitate will dissolve in dilute ammonia, so you'd add dilute ammonia first. If your precipitate doesn't dissolve in dilute ammonia, you would then add concentrated ammonia, because silver bromide will dissolve in concentrated ammonia. If your precipitate still doesn't dissolve in concentrated ammonia, this means you must have got the silver iodide precipitate, because that does not dissolve even in concentrated ammonia. To test for carbonate ions, you would add a dilute acid, which would react with the carbonate ions to form carbon dioxide and water. The carbon dioxide is produced as a gas, so you would see fission in your sample, and you could then verify the result that the gas that you produced was carbon dioxide by collecting the gas, bubbling it through lime water, and if it goes cloudy, that confirms that the gas you produced was carbon dioxide, therefore the ions you had in your original sample must have been carbonate ions.